In this video, we now want to start looking at vectors. What is a vector and what to do with a vector once we have it. Now, a vector is simply an object that lives in a coordinate plane. This is where the issue of direction comes from, right? Vectors have magnitude and direction, and you cannot have direction unless it's specified with respect to some coordinate axis, okay? So imagine that I have an x and a y axis here, and I have a vector A that I've labeled here. Now, a vector is going to have what we call components in general. Now, a vector that has components, we say that the components live in the x direction and they are in the y direction. So this complete vector A is going to be made up of the components in the x direction and the components in the y direction. We typically call it a sub x and a sub y. Now, this I hat and this j hat here are what we call unit vectors. And the ax here specifies the magnitude of my component vector in the x direction, and the I hat here specifies that that magnitude is in the x direction. And the j hat here specifies that that magnitude is in the y direction. So a unit vector is simply a vector with unit length. In other words, it has a length of 1 in whatever units you are in. So for instance, if your axes are in velocity of meters per second, then your unit vector would have a magnitude of 1 meter per second in the x direction and in the y direction. So it essentially assigns the direction to the magnitude of ax. So ax, the symbol ax, is just a magnitude. It does not have direction associated with it. Its direction is put in by the unit vector here, or ay is the direction of ay is put in by the unit vector here. Okay, so we can write a vector in this form, right? So a vector is simply the sum of its x and its y components, which I have labeled here, right? So we have ax and we have ay here. Now, there are essentially two things you may want to do with an individual vector. And those are, if I have the components, I want to calculate the magnitude of the actual vector, and I might want to find its direction, okay? And those are the two things that make up a vector, magnitude and direction. And unless otherwise specified, the direction is going to be specified with respect to the x-axis, okay? Our angle theta is going to be specified with respect to the x-axis. Once I know the magnitude of this vector and the angle that it makes with the x-axis, once I know those two things, I know everything there is to know about this vector, okay? There is only one unique vector with those two characteristics. So if I'm given the two components along my axes, I can then find my magnitude and my angle. Okay, so that's what we'll do first, and then we'll do the reverse, where if I'm given the magnitude and the angle, what if I just want to simply find the components, my x component and my y component, all right? So, as you can see, my individual components make a right triangle. And this is because the x and the y axes are perpendicular to each other. So if my x component lies along the x-axis and my y component lies along the y-axis, they will be, by definition, perpendicular. So they will make this right triangle, and my magnitude of my a vector here is going to be the magnitude. So I need to calculate the hypotenuse. A represents the hypotenuse of this right triangle, so I need to calculate the hypotenuse, and that will give me the magnitude of A. So what I do is the magnitude of A I write as the absolute value of A. Okay, so the absolute value of A is simply going to tell me the magnitude. And I calculate this using the Pythagorean theorem. So this is just going to be the component in the x direction squared plus the component in the y direction squared. And in this case, we're going to have ax is just 6 units. And again, the units here are arbitrary. I'm not necessarily in any given unit system. Your vector could be in length, in millimeters, centimeters, meters, kilometers, miles. It could be in speed, or technically velocity. It could be in centimeters per second, meters per second, kilometers per hour, miles per hour, furlongs per fortnight, whatever the case may be. It could be in acceleration, meters per second squared. It could be in force, newtons or pounds, whatever the case may be. All right, so here I'm just going to have 6 units squared and 6 units squared. And here we're going to have 36 plus 36 gives me 72. And the square root of 72 is roughly 8 point something. I don't have my calculator right in front of me. But if you put in your calculator, take the square root of 72, you're going to get 8 point something. Probably along the lines of 8.6 or so. All right, so that takes care of the magnitude. This is how you calculate the magnitude if you're given the 2 individual components. Okay. Now, what about the angle? Well, now that we have the angle, we have all of the trigonometric functions open to us. We can use sine, we can use cosine, or we can use tangent. Actually, specifically, we're going to use the inverses of those. And what it's customary to do, once you have your components, it's customary to take the arctan or the inverse tangent. So, theta can be written as the inverse tangent of my y component over my x component. And so this is going to be the inverse tangent, in this case, of 6 over 6. And of course 6 over 6 goes to 1. And the arctan of 1 is 45 degrees. Okay. Now, I don't care if you use radians or degrees. It does not matter as long as you're aware of which system you're in. Okay. If you think you're in degrees and you get a very bizarre answer here of like 0.8 something or whatever, then you're likely in radians, and you just need to recognize the fact. I don't care which system you use. For the most part, early on, we're going to typically use degrees in these videos. Once we get to things like rotational motion and torque, we will transfer over to the radian unit. But for now, it does not matter which system you're in. So now I have uniquely specified this vector. I have calculated its magnitude, whatever the square root of 72 is, okay? So the magnitude of A we found to be the square root of 72, and the angle with respect to the x-axis was 45 degrees. Now there's only one vector that fits both of these criteria. So here we have the magnitude, and here we have the direction. So we have now uniquely specified this vector. Now what about the opposite process? What if we're given the magnitude and the angle, and we want to find the 2 individual components? So now let's turn this on its head a little bit and imagine that scenario. So now let's say we're given the situation where we have our 2 axes, and I'm just going to draw a general vector here, and I'm going to specify that it's 6 units in magnitude. Okay, it has 6 units in magnitude, and it makes an angle with respect to the x-axis of 30 degrees. Okay, now I want to know what is the x component along the x-axis here, and I want to know what the y component along the y-axis is. Now, technically, this arrow should exactly hit up here. My drawing is not perfect, but you get the idea. So I want to know what AX and AY are. Okay, so to get AX and AY, well, if all we're given is the hypotenuse, then as far as solving at least for one of these, I have to use either sine or cosine. Nothing else is open to me because I only know the hypotenuse and the angle. And the only trig functions that have the hypotenuse and an angle are sine and cosine. Tangent does not involve the hypotenuse. And I'm ignoring the secant, cosecant, and cotangent for now. All right, so AX, we need a function that relates AX theta, and a, and that turns out to be the cosine function. Cosine of theta is adjacent over hypotenuse, so this is going to be ax over a, and if I multiply both sides by a, then that gives me ax. Ax is equal to the magnitude of a times the cosine of theta. So my x component in this case is going to be found by multiplying the magnitude of a, my 6 units, by the cosine of theta. Whoop. And similarly, I can do a similar process and show that ay is going to be a times the sine of theta. So what is ax in this case, right? So ax is going to be calculated as the magnitude of a, which is 6 units, times the cos of 30 degrees. And the cos of 30 degrees is the square root of 3 over 2. If I plug this into my calculator, I get like 0.86 something or other with a long string of decimals, but at the end of the day, it's the square root of 3 over 2. Okay, the 2 is not inside the square root. So this is the same thing as 3 times the square root of 3. Okay, that's the magnitude of my vector along the x-axis. And my y vector is going to be 6 times the sine of 30, and the sine of 30 is 1/2. All right, so the sine of 30 is 1/2. And if I multiply 6 and 1/2, I get 3. So now I have my x and y components. I can now write my vector in terms of the magnitudes of its components and its unit vectors as 3 square root 3 in the x direction, or I hat, plus 3 in the y direction, or j hat. So this is now my vector. These represent the magnitudes of the components, and the directions are specified by my unit vectors. In the next video, we'll talk about vector addition and subtraction. Stick around.